Today is L'Hopital and indeterminate forms. We will be learning a new way to solve a limit using L'Hopital's rule. Okay, so an indeterminate form is exactly what it sounds like. It's that it's an equation where we cannot determine or guarantee a limit. Okay, so indeterminate forms are things like 0 over 0, infinity over infinity, infinity over infinity, 0 times plus or minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0, infinity minus infinity, and then and that's it. Okay, there might be other ones, but those are some of the common ones. The ones that we see most often are our 0 over 0 and infinity over infinity. So let's look at this example. We're going to find the limit using direct substitution. Okay, so I'm going to say this is e to the 2 times 0, which is 0, minus 1, over e to the 0, minus 1. So I get 1 minus 1 over 1, over 1 minus 1, which gives me 0 over 0. And what I see is that this is the indeterminate form. Okay, so what do we do? Normally what we would do is we would try and simplify this expression by factoring, mostly by factoring, okay? Or by multiplying by like a complex conjugate or something, which is fine, but another method is we're going to apply L'Hopital. It looks like L Hospital. L'Hopital's rule, okay? So L'Hopital's rule says that if we get a limit and we get the indeterminate form of 0 over 0 or infinity over infinity, then we can take the derivative of the numerator, so f prime of x, and the derivative of the denominator, g prime of x, and then take the limit of that. You can actually apply L'Hopital's rule again. This is equal to the limit as x approaches c of f double prime of x over g double prime of x, if needed, okay? So let's do a couple to practice. So here's the indeterminate form, 0 over 0. This is what we do, is we apply direct substitution, okay? So e to the 0 minus 1 over 0. So I get 1 minus 1 over 0, which is 0 over 0. Okie doke. So I see that what I end up with is the indeterminate form. So I can just leave that 0 over 0. And then what I need to say is I'm going to apply L'Hopital's rule, or apply L'Hopital, okay? So I'm going to write the limit as x approaches 0, and we take the derivative of e to the 2x. So derivative of the numerator is e to the 2x times the chain, which is times 2, and then the derivative of negative 1 is 0, all over the derivative of x is 1. So I end up with, now I don't have an x in the denominator, so I'm just going to apply direct substitution, and I get direct substitution. I end up with 2 times e to the 0, which is just 2. So the limit as x approaches 0 of e to the 2x minus 1 over x is actually 2. Okay. All right, let's do this again. So direct substitution, I usually just write arrows here. Okay, so the limit, or we're doing the ln of infinity over infinity. So ln, remember it looks like that. So as x goes to infinity, y goes to infinity. So this is going to end up with infinity over infinity. That's an indeterminate form. So we're going to apply L'Hopital. So the limit as x approaches infinity of, and we're going to take the derivative of ln of x, which is 1 over x, over the derivative of x, which is 1. So now I end up with 1 over infinity, which goes to 0. Okay. All right, next up. We have, sometimes we have to apply L'Hopital more than once. That's okay. So let's direct substitute in that infinity. So negative infinity squared over e to the negative negative infinity, which gives me infinity over e to the infinity, which is infinity over infinity. Indeterminate form, we apply L'Hopital. Okay, so next we take some derivatives. The limit as x approaches negative infinity of, okay, the derivative of x squared is 2x. Derivative of e to the negative x is negative e to the negative x. And then I am going to direct substitute. So I get 2 times negative infinity over negative e to the positive infinity. So again, I end up with infinity, basically negative infinity over negative infinity. Eek, that's an indeterminate form. Okay, let us turn off our notifications. Let's try that. Okay, and then we apply L'Hopital again. Okay, so I'm going to take the limit as x approaches negative infinity. This time we're going to take the derivatives of the derivative, so the second derivative, I guess. Okay, so the derivative of 2x is 2. The derivative of negative e to the negative x is, well, e to the negative x stays the same, and then we bring down the negative, so it's going to end up being a positive, a negative times a negative. So I can go ahead and plug in my direct substitution now. So I have 2 over e to the negative negative x, so, or negative negative infinity, which is positive infinity. And again, e looks like, e to the x looks like this. So as x goes to infinity, y is going to infinity. So this is basically 2 over infinity, which is 0. All right, so the limit as, I guess I could rewrite it. The limit as x approaches infinity of x squared over negative infinity, e to the negative x is equal to 0. All right. So this one is a different kind of indeterminate form, 0 times infinity. So we always have to try and direct substitute. So I'll go ahead and do that. This is e to the negative infinity times the square root of infinity. E to the negative infinity is 1 over e to the infinity times the square root of infinity, which gives me, this is basically 0 times the square root of infinity, which is just infinity. Okay, so we're going to end up using, this is an indeterminate form.
Okay, so since we got the indeterminate form of 0 times infinity, what we need to do is rewrite our limit in a fraction. So we're going to say the limit as x goes to infinity of the square root of x, so x to the 1/2 power, over e to the x, since we have our negative exponent. Okay, and now I have my fraction. So I'm going to direct substitute again, just to double check to make sure we get an indeterminate form. Okay, so I get infinity over infinity. So indeterminate form, we're going to apply L'Hopital. Okay, so I can take the limit as x approaches infinity of the derivative of the top. So that would give me 1/2 x to the negative 1/2 over e to the x.
Okay, for ease, I'm going to rewrite this as the limit as x goes to infinity of 1 over 2 because of the 1/2, and then the x to the negative 1/2 will go to the denominator, and then I have e to the x. So when I direct substitute, I get 1 over 2 times infinity to the 1/2 e to the infinity. That's all going to evaluate to 1 over infinity. And 1 over infinity is basically 0. Okay, so the limit as x approaches infinity of e to the negative x times the square root of x is equal to 0. Okay. Last one, we're going to look at the indeterminate form of 1 to the infinity. And so let's go ahead and do this. We have the limit as x goes to infinity of 1, the quantity 1 plus 1 over x raised to the x power. And since I have our x raised to an x, we're going to go ahead and let's go ahead and make sure we are in do not disturb mode. And then we will also set this limit equal to y. And so we can take the ln of both sides and get that exponent out of the exponent. Okay, there's one thing that I noticed first right off the bat is that this 1 plus 1 over x to the x, as we split this 1 into an infinite number of times, you may recognize this as the limit that gives us e. So this, remember with our compound interest, that this, if I split the rate infinitely, we end up with the value e. So we're going to prove that this special limit is equal to e. Okay, so I have y is equal to the limit as x approaches infinity of 1 plus 1 over x raised to the x. And then we're going to take the ln of both sides so that I can get the x out of the denominator. Okay, so what I know is that the ln of the limit and the limit of the ln are the same. So I am going to write this as the ln of y is equal to the limit as x goes to infinity of the ln of 1 plus 1 over x to the x. And then using my power property, we're going to pull that x to the front. So the ln of y is equal to the limit as x goes to infinity of x times the ln of 1 plus 1 over x. Okay, and so next up is we're going to take a look at what the limit of, we're going to like evaluate this limit. And what I get is, well, let's do it on this side. We're going to direct substitute, and I get the limit as x approaches, or actually, I'm going to just plug in, substitute in infinity and for x. So I get infinity times the limit of 1 plus 1 over infinity. That's 0. So the limit of the ln of 1 is 0. So this would be infinity times 0, which is an indeterminate form. So we know that we can apply L'Hopital, but we need to get this into a fractional form. So what we'll do is bring down the ln y, and I'm going to write my limit as x approaches infinity. So I need to change what's inside this parentheses business into a fraction. So I'm going to do that by keeping the ln, this is a fancy trick, of 1 plus 1 over x. And then I can rewrite x in the denominator as 1 over x. Okay, like if I wanted to get that out of the denominator, remember you would just multiply the numerator and the denominator by x over 1, and it preserves the form. Okay, so we're like unsimplifying. Okay, when I use direct substitution, I get the ln of 1 over infinity. That is 0, so I get 0 over 0, again, which is an indeterminate form. So I can apply L'Hopital. So we're going to apply L'Hopital. So I'm going to take the ln of y is equal to the limit as x approaches infinity of the numerator, the derivative of the numerator, which is 1 over the input of the ln, so 1 plus 1 over x, times the chain, so times negative x to the negative 2, okay? And then we need to take the derivative of the denominator, which is x to the negative, really that's x to the negative 1. So again, that would be negative x to the negative 2. And I notice that these are going to cancel, okay? And then what I end up with is just the ln of y is equal to the limit as x approaches infinity of 1, just the numerator, so 1 over 1 plus 1 over x. And then we're almost there. Okay, now we're going to direct substitute. We'll direct substitute the infinity in. So I get the ln of y is equal to, I'm just going to write direct substitute. 1 over 1 plus 1 over infinity. And 1 over infinity we know goes to 0. So I just end up with the ln of y is equal to 1 over 1, which is 1. Okay. And then I have to solve for y, because what I did at the very beginning is that I set this limit equal to y. So I need to isolate y to figure out what this value is going to be. Okay. So how do we isolate y? We use snail method because the y is the input. So, or you can take the raise both sides to e, but we're going to say snail method. E to the 1 is equal to y. So what is y equal to? E to the 1. So all in all, we started out with y is equal to the limit as x approaches infinity of 1 plus 1 over x to the x. And we now know that this special limit is equal to e. And this is why we didn't derive this in pre-calculus. Okay, so this is one of those limits you can remember now that we've done we've derived it. Okay, cool.